um, Hamiltonian vector fields on contact manifolds, which probably you are familiar with, or maybe some of you, and these evolution vector fields. And for the last part, I will be briefly sketching some applications in thermodynamics in very simple systems. Okay, so in this talk, eta will be a contact manifold and eta its contact form, and R will be the red vector field. That is, M is a 2n plus 1 dimensional manifold. Eta is the contact form, which is just a one form that satisfies that eta product the eta to the n is a volume form. That is, it doesn't vanish at any point of the manifold M. And R is the red vector field is the only vector that is in the kernel of the differential of eta, and that applied to eta gives 1. Okay, in these manifolds there is a Darboux theorem, and you can always pick local coordinates qi, pi, and z, such that the contact form and the red vector field have this aspect. An example of a manifold which has a natural contact structure is a cotangent bundle times R. As eta, you take the set, where set is the R coordinate, minus the pullback of the Liouville one form of the cotangent bundle, which in bundle coordinates writes as this. Okay. In a contact manifold, you can define this isomorphism of modules from vector fields to one forms just by contraction on the eta plus contraction on eta times eta. And this isomorphism takes the red vector field onto the contact form. Also, a contact manifold, I won't comment on this very much, but a contact manifold is an example of a Jacobi manifold, and it has a Jacobi structure which is composed by one bivector lambda and one vector field which is minus the red vector field depending on your sign conventions, but we choose this one. And it is defined as this, is minus the differential of eta composed with the inverse of this isomorphism. You can use this bivector or this Jacobi structure to define a Hamiltonian vector fields for functions. Okay, and the definition of the Hamiltonian vector field is just this one, is just the bivector contract with the differential of the function minus h times the red vector field. Okay, but we can also define this other vector field that we have called the evolution vector field, and we have introduced on an article on this year, which is just with the bivector. You don't have this term with the red vector field. In local coordinate has the same expression for in the qi and pi components, but this should be a set. Sorry. On the last component, depending on set, you have, well, this is different, right? In the Hamiltonian vector field, you have pi, the h to pi minus 8, and in the red vector field, you don't have this 8. Okay, so I will compare the properties of these two vector fields. One property, the Hamiltonian vector field, in general, does not preserve the energy of the system. The energy dissipates along the integral curve of the Hamiltonian vector field. This is with this expression, but the evolution vector field does preserve the energy. Another difference is that the Hamiltonian vector field does not preserve the contact form exactly, but you multiply it by a constant. It's what we call a conformal contactomorphism. The flow of this Hamiltonian vector field will be scaling the contact form, multiplying it by a function. But the evolution vector field does not. It has this extra dh term. And one last difference is the tangency to the kernel of the contact form. The, the Hamiltonian vector field is not tangent to the kernel of the contact form, but the evolution vector field is. We will see how this property will be important for the applications in thermodynamics. Okay, now I will briefly comment on some way to understand the dynamics of these two vector fields. Okay, now iota sub c will be the canonical inclusion of the constant energy C level set. Okay, we will assume that C is a regular value, so this is a hypersurface. H to the -1 of C is a hypersurface, and we will define on this hypersurface this should be an I star here. We will define the pullback of the differential of theta to that hypersurface, which is a symplectic form, indeed an exact symplectic form, because it is the differential of the pullback of eta. Okay, and in this exact symplectic manifold, we have a Liouville vector field, which is defined as this. The only vector field that contracted with the one form, with the two form, gives you the two form. And this vector field satisfies that the derivative of the symplectic form is the symplectic form. Okay, so now with this terminology, I will compare the dynamics of these two vector fields. This is a theorem by Alessandro Babetti, Manuel León, Marrero, Edith Padrón, where this says that in a contact manifold, the contact Hamiltonian vector field, you can divide the space onto submanifolds. One is where the energy is not zero on that submanifold. And then the Hamiltonian vector field is just the red vector field for this modified contact one form. Okay, and in the zero level set of the energy, then the contact Hamiltonian vector field is a reparametrization of, well, the flow of the contact Hamiltonian vector field is a reparametrization of this Liouville vector field. Okay, it's just a multiple of the red vector field. Okay, however, for the evolution vector field, if you restrict it to any level set, to any constant energy hypersurface, then it is a reparametrization of the red vector field at any level, not only at the, I mean, it's a reparametrization of this Liouville vector field at any level set, not only at the zero level set. Okay, now I will discuss the Lagrangian formalism. As I commented before, the cotangent bundle times R has a natural contact structure, but the tangent bundle times R does not. However, if you have a Lagrangian function, you can a contact structure is naturally induced. This is similar to what happens on the symplectic theory. We need a regularity assumption on the Lagrangian, which is just that the Hessian matrix with respect to the velocities is regular. And we can define a Fourier transform in this setting, which takes the contact form of the cotangent bundle onto the contact form of the tangent bundle if everything is regular. And from the Lagrangian, we can construct an energy function with this delta is the Liouville vector field, which in bundle coordinates can be written as this. Okay. I think you don't see the text above. Anyway, from this, we can compute the Hamiltonian vector field and the evolution vector field with respect to this one form, eta sub L, by constructing the bivector and just the same as before, as in the Hamiltonian case. And I will call this vector field the Lagrangian vector field and the evolution Lagrangian vector field. And I will denote them by lowercase chi for the Lagrangian and uppercase chi for the evolution. And the Fourier, the Lagrange transform, the Legendre transform works as it should. It takes one vector field onto the other if the Lagrangian is regular enough. Okay, so both vector fields are second order differential equations. This can be characterized as many in many ways, but one way to characterize it is that its integral curves always satisfy that the velocity, this vi in bounded coordinates, is the time derivative of qi. Okay, and for the Lagrangian vector field satisfy the Herglotz equations, which are the ones over here, and the evolution Lagrangian vector field satisfies this modified equation, the evolution Herglotz equation. You see, the equation above is the same, but they have a different equation for the set variable. They also satisfy minimum principles. The Lagrangian vector field satisfy the Herglotz variational principle that can be written as this, which is kind of a Bakonomic principle. We will consider the space of curves, which from the closed interval 0t to q times r, such that they have boundary conditions for the q part and for the z part only an initial condition. Okay, and now we will restrict this space of curves to the one that satisfy this differential equation over here. Okay, now we can define the action, or we will define it only on this restricted space of curves satisfying this equation to be the endpoint of the set variable minus the initial point, or equivalently by the fundamental theorem of calculus, the integral of the Lagrangian along the curve on Q, its derivative, and this set curve. Okay, as you see, this generalizes the Euler-Lagrange principle in case that if L does not depend on set, and this is kind of an implicit principle. The action is kind of, you can think about this set variable as the action itself. Anyway, okay, and the theorem is that a path is a critical point of this action if and only if Q dot, and set is a solution of the Herglotz equation. Okay, now I will introduce this variational principle for the evolution vector field. This is a non-holonomic principle, but this is a nonlinear non-holonomic principle. I will later comment in which sense. Okay, we consider again the space omega of curves with the end boundary conditions on the curve on Q, and when the initial condition with the curve on Q dot. And now we restrict it. The restriction we do is we want our curves to be tangent to the kernel of the contact one form, and in coordinates is at this. Also, we will restrict the space of variations. The space of variations also, we will only consider the variations which are tangents to the kernel of this contact distribution, of this contact form. And we define the action now on the whole space, not only on the restricted space. And the theorem is that a path on the restricted space satisfies that if the differential of the action at that path vanishes with any of these admissible variations, which are the variations I remember, which are tangent to the kernel of the contact form. If and only if Q, Q dot, and Z are a solution of the evolution Herglotz equation. I must remark that this non-holonomic principle, this nonlinear non-holonomic principle, is not ZF's principle, which is probably the most famous one, but is one of a more general kind, what was studied already in 2004, maybe even earlier, by Sendra, Alberto Ibor, Manuel de León, David Martin, and it is used, this is very similar to the one which is used by Guy Balmaz and Yoshimura on their theory, on their variational theory of non-equilibrium thermodynamics. Okay, now I will just briefly comment on applications to thermodynamics. We will describe thermodynamic processes as curves on this space, which is a contact manifold, and they will be integral curves of an evolution vector field. First, we will consider systems that are simple. This means that they can describe through a unique thermal variable. We will choose the entropy, that this will play the role of this set variable, and a finite number of mechanical variables, which will be positions and momenta, or we can do positions and velocities if we want to work on the Lagrangian formalism. And we will also assume that the system is isolated. That means that there is no exchange of matter or energy with its surroundings. Okay. The thermodynamic space is equipped naturally with two one-forms. The heat form, that, as we said, that our system is simple, has to have rank 1. So we can write it as TBS, okay, because it has rank 1. And a rank n work form, which we can write it as pi dqi because of its rank, where these pi are usually interpreted as pressures. Okay, the first law of thermodynamics says that for a closed system, which is a system with there is no exchange of matter, and ours is because it does not exchange matter or energy, along the process, we need that the variation of the energy equals the heat minus the work. Okay, but since the system is also isolated, the energy, the total energy cannot vary. So if we divide it by this T function, which will be the temperature, of course, and we define this Pi equals the pressures divided by the temperature, then this process chi satisfy the first law if and only if it is tangent to ker eta, where eta is precisely this contact form, which is the natural contact form of this cotangent bundle times r. And well, the proposition is that the integral course of the evolution vector field satisfies the law of thermodynamics for isolated systems. Indeed, it preserves the energy and it is tangent to the contact form. Okay, and last of all, I will discuss the second law. The second law is easy to see in this context. It's just that for an isolated system, the entropy increases, but if you just saw the aspect in coordinates of the evolution vector field, it's easy to see that it is equivalent. Sorry, this is the Liouville vector field on the Lagrangian side, which is pi partial of pi of h. Okay, so if this is positive, then the second law is satisfied. For example, Hamiltonians of this type satisfy the second law for all their processes if this G is a positive semi-definite. Okay. Now, just to give a simple example, I will I will choose a linearly damped harmonic oscillator, with the Hamiltonian just has this aspect. This is the kinetic part. This would be the potential part, and this would be the internal energy. The equations of motion are just like this, and on the you can also write a Lagrangian, and you can solve this maybe numerically. It has this aspect, the position with respect to time, and this is the entropy. I didn't in this in the last article we wrote about this. There is more things that I left out of this talk. One is we have a bracket formalism similar to the one generator bracket, which is related to the bracket of the Jacobi structure, but it is not exactly that one. And we created two classes of numerical integrators. One based on discrete gradient methods by discretizing this bracket, and another one based on variational methods by adapting a method which was used to integrate the Herglotz, well, the Lagrangian vector field through the Herglotz principle. And this is it. These are some references I used in this talk. And if you have any questions, I would be very happy to answer them.
Thank you very much.